Welcome to the section for examples for mathematical proofs. So in this section, we will work out 6 example problems. So let's take a look at the first problem we have. The first problem says to let a, b, c, and n be natural numbers and the greatest common divisor of b and n be 1. So we are asked to prove that if a divided by b is logically equivalent to c modulus n, then a squared divided by b squared is logically equivalent to c squared modulus n. Okay, let's write our proof for this. So we are going to let a, b, c, and n be natural numbers, and the greatest common divisor of b and n be 1. So let's suppose, by way of contrapositive, that a squared divided by b squared is not logically equivalent to c squared modulus n. So then we have a squared is not logically equivalent to b squared times c squared modulus n. And thus, a is not logically equivalent to b c modulus n. So therefore, a over b is not logically equivalent to c modulus n as desired. And that basically is how we go about solving this by using proof by contrapositive, because we're just looking at the contrapositive of this statement and evaluating it just like you would a direct proof, except you're looking at the contrapositive statements. And I don't know if doing a contrapositive for this would be quicker than doing the direct proof. Not for this particular problem, but it is nice to see the logic that the contrapositive can prove this statement just like the direct proof can. The second problem gives us this statement: let U be the universal set and the set A1, A2 up to AI be a subset of the universal set. So we are asked to prove that if the index union of sets AI equals the empty set, then the complement of the indexed union of sets AI equals the universal set. Okay, so let's write out this proof. So let U be the universal set and A1, A2 up to AI be subsets of the universal set. So let's suppose, by way of contrapositive, that the indexed union of sets AI is not equal to the universal set. So then the index union of sets of AI is non-empty. So therefore, the indexed union of sets of AI is not equal to the empty set as desired. And we're going to close this one with an O, B, I, D, I. And if you remember from section 3, this means, oh boy, I did it. We did it. We did it. We wrote out the proof for this problem. I was waiting for the chance to get to use one of these, and I thought that now would be a good time to use it. Now let's take a look at problem 3. For problem 3, we are given let x be an integer, and we are asked to prove that if 7x plus 3 is even, then x minus 3 is even. Okay, let's take a look at the proof for this. So we are going to let x be an integer. So let's suppose by way of contrapositive that x minus 3 is odd. So then we have x minus 3 equals 2k plus 1, where k is an integer. So we have x equals 2k plus 4. So we'll add the 3 on the other side. So now let's plug in x into 7x plus 3. So we have 7 of 2k plus 4 plus 3 equals 0. And whence we have 14k plus 28 plus 3 equals 0. So now we have 14k plus 30 plus 1 equals 0. And thus, we can factor out a 2 from the first two terms. We have 2 times 7k plus 15 plus 1 equals 0, where 7k is an integer. So therefore, 7x plus 3 is odd, as desired. So essentially what we did was we assumed by contrapositive that that the x minus 3 was odd, and we set it equal to the set of odd integers 2k plus 1. We found what x is, plugged it in, and then showed that 7x plus 3 is of the form of an odd set of integers. And I guess technically, and I'm not sure why I wanted to specify this in this proof, but this line could probably be omitted because we already have k defined as an integer, and it should be logically understood that 7 times k would produce an integer. But yeah, that's pretty much it for the third problem. Now let's take a look at the fourth problem. For the fourth problem, we are given the statement, let x and y be integers, and we are asked to prove that if x and y have opposite parities, then 9x plus 7y is odd. Okay, let's take a look at this proof. So we are going to let x and y be integers, and we proceed by cases on x and y. So the first case, we are going to let x be even and y be odd. So then we have x equals 2k and y equals 2j plus 1, where k and j are integers. So we plug everything back in. We have 9 times 2k plus 7 times 2j plus 1, which equals 18k plus 14j plus 7. But we can rearrange and write it as 18k plus 14j plus 6 plus 1. And then we can factor out a 2 from the first three terms, and that gives us 9k plus 7j plus 3 plus 1. And this is the form for an odd set. So therefore, 4x plus 7y, 9x plus 7y is odd. All right, so let's look at the second case. So we are going to let x be odd and y be even. So then we have x equals 2k plus 1 and y equals 2j, where k and j are integers. So we plug everything back in. We have 9 of 2k plus 1 plus 7 of 2j. We distribute everything. That gives us 18k plus 14j plus 9. Then we can rewrite it to be 18k plus 14j plus 8 plus 1. And that will give us, we'll factor out 2. We have 9k plus 7j plus 4 plus 1. Again, the form of an odd set. So therefore, 9x plus 7y is odd. And that's it for the proof. We've looked at all the cases that we can for x and y having opposite parities. So we will close out this proof with an A, T, W, F. And if you remember from section 3, this closing means awesome. That was fun. Now let's take a look at problem 5. For problem 5, we are given the statement, let A and B be sets. We are asked to prove that if A is a subset of B, or the power set of A is a subset of the power set of B, then the power set of the Cartesian product of A and A is a subset of the power set of the Cartesian product of B and B. Okay, so let's write our proof for this. So we are going to let A and B be sets, and we proceed by cases. Okay, for case 1, we are going to let A be a subset of B. So let's suppose that x, y is an element of the Cartesian product of A and A. So then x is an element of A and y is an element of A. So since A is a subset of B, x is an element of B, and y is an element of B. So xy is an element of the Cartesian product of B and B. So thus, the Cartesian product of A and A is a subset of the Cartesian product of B and B. So therefore, the power set of the Cartesian product of A and A is a subset of the power set of the Cartesian product of B and B. Okay, let's look at our other case for this problem. Let's look at our second case, case 2. So we are going to let the power set of A be a subset of the power set of B. So since A is an element of the power set of A, then A is an element of the power set of B. So thus, A is supposed to be capital A. Let's do since, let's write it like this. Since A is an element of the power set of B, A is a subset of B. Because you remember that's the definition of a power set. It's the set of all the subsets of B. So since A is an element of the power set, it is a subset of B. So now we'll kind of do the similar steps like we did for the first case. We're going to suppose that X and Y are an element of the Cartesian product of A and A. So then X is an element of A and Y is an element of A. So since A is a subset of B, X is an element of B, and Y is an element of B. So the element XY is an element of the Cartesian product of B and B. And thus, the Cartesian product of A and A is a subset of the Cartesian product of B and B. So therefore, the power set of the Cartesian product of A and A is a subset of the power set of the Cartesian product of B and B, as desired. And that is all we needed to do for this proof, because we were given the two conditions that if A is a subset of B, or the power set of A is a subset of the power set of B, that the power set of the Cartesian product of A and A is a subset of the power set of the Cartesian product of B and B. So we just needed to do two cases and look at both of the conditions we were given to determine that yes, this theorem is true. Now on to the last problem for this example problem set. For problem 6, we are asked to evaluate the following proof. And the result is that let x and y be natural numbers. So then x divided by y is an integer if and only if y divides x. Okay, so the proof opens by defining x and y as natural numbers, and then it looks at one implication of the biconditional, and it says that suppose by way of contrapositive that y does not divide x, so then x is not equal to yk, where k is an integer, and therefore x divided by y is not equal to k, and x divided by y is an integer. And then we look at the implication let y divide x, so then x equals yk, where k is an integer, so therefore x over y equals k, and x over y is an integer as desired. Okay, so there are a few things about this proof that make it incorrect. So let's write out our proof evaluation. So, although the proof did correctly attempt to evaluate the biconditional, it only evaluated one way, by looking at the contrapositive and direct proof of the implication y divided by x if y divides x, then it implies that x over y is an integer. So instead, both implications both implications x over y is an integer implies y divides x, and y divides x implies x over y is an integer, should be evaluated or both of their respective contrapositives. So from what we just wrote here about this proof evaluation, what are we saying is wrong with this proof? So let me try to make a better diamond. So when you look at this proof, yes, you do have a biconditional, or at least it's trying to evaluate it from a biconditional, but it's technically only evaluating it in one direction by looking at the implication y. If y divides x, then x over y is an integer. And this person looked at the contrapositive and the direct proof of just that implication. And that's not the correct way to evaluate this biconditional statement, x divided by y is an integer if and only if y divides x, because you're technically only looking at one direction, and you're just looking at it using two different proof techniques, which you don't even need to do. You can just do one proof technique. And it's important too that when you do a biconditional, you stay consistent with your proof techniques throughout. So if you're looking at the contrapositive on one end, then you need to look at the contrapositive on the other end. And that's basically what we were implying in this proof evaluation. Okay, that is it for the section 4 example problems for mathematical proofs. Thank you guys so much for watching, and I will see you in section 5.